Welcome, everybody. Thank you for joining today's webinar on package product drop testing applications presented to you by Lansmont. Lansmont is a proud member of the Physical Properties Testers Group, a collective of specialized brands in physical properties testing. PPT covers areas such as tensile and compressive strength, torque testing, textile analysis, and real-world dynamics like shock and vibration. Alongside Lansmont, our family of brands includes McMesson, James Hill, and Telluris. To learn more about PPT or our individual brands, visit the PPT site or check out our on-demand content. A link is available in the chat box for your convenience, so you should be able to grab it from there. Many of you already know our host, Eric Jonassen. I'm Sharon Smorenberg, one of today's organizers, and we're supported by a dedicated team across the United States, Europe, and Asia. As always, we encourage you to ask questions. You can do it throughout the webinar. Just use the question box to submit any queries you have. We'll address them at the end of the session. The webinar, again, is being recorded, and you'll get the recording via the email that you registered with. So feel free to share that recording with any colleagues or interested parties who couldn't attend or just would like to know more about drop testing. And for now, I'll hand you over to Eric.
Okay, thank you, Sharon. Appreciate the introduction, and thanks for your support as we move forward here this morning, or today, I should say. And I'm going to go ahead and turn my camera on real quick for the start of the webinar, just to introduce myself quickly. Takes a minute apparently for the camera to come on, but hi everyone, good morning, good afternoon, and good evening probably to some folks. I actually am doing this webinar remote, which is a little bit outside my norm, not doing it in my office. I'm actually at Virginia Tech University in Blacksburg, Virginia, doing some different work or additional work related to some of our equipment here. So I'm actually doing a webinar on the road, so I apologize if it looks or sounds different doing it right from a laptop from a remote location, but I think it's going to work fine. And just want to say hello before I jump into it and turn my camera off for the rear of the session as we talk about drop testing. Just joked my colleague Sharon about doing delivering this session on drop testing, which I said after 35 years, to think that I'm still just talking about things like dropping boxes is, I don't know if that's a good thing or a bad thing, jokingly speaking. For what it's worth, I still do enjoy it quite a bit. So I'm going to spend the next half hour or so talking about dropping things and the drop testing application itself. So I'm going to turn my camera off and get going. I have videos that I'm going to be using as part of my presentation, and what I find, and that what we found is that using the videos or sharing the videos through the GoToWebinar app that we're using now is a little bit clunky. So it continues to be the case, still trying to figure it out, but bear with me with the videos. I think they still make the point, even if they're a little bit rough as far as not playing smoothly, but I promise that at the end of it, like I do with all my webinars, is that with the recording, I go back in and overlay the high quality videos on those recordings. So anything that looks semi-interesting would be more interesting, even more interesting in the recording. So as we talk about drop testing, it's kind of common for folks to think about, I don't know, maybe the traditional parcel delivery guy who does the abuse to your packages, right? When they're delivering them, that's walking them around, that's banging them around, that's dropping them, that's throwing them. It's humorous. I thought I'd start with one little bit of humor as part of the presentation, but that's kind of what we think of when we think of dropping boxes or any type of drop testing procedure. We think, well, it's because packages get dropped in the real world, right? And the fact is, yeah, they do. They can and they do. but there are other things that can happen in the supply chain that imparts shock or impacts, some type of impact energy to packages that, and they might come from drops, but they might come from a number of different types of dynamics, which I'll talk about moving forward. But even though this video was humorous, this next video is real. Okay, so this is something I've shared in past and other presentations as well. But this is actually a camera that was capturing some video at the Pudong airport in Shanghai, China, and this was a number of years ago, but related to an Intel shipment. So you think, well, people don't really drop boxes that high, do they? Well, this is an example of reality. Okay, so this was people walking on top of a big ULD or a unit load that was shipped by air cargo, and the way they were unloading it was dropping packages. And this is one that was just from a few years ago, showing Amazon packages being tossed out of a train, a transport cargo train in India. And so you think, yeah, that silly stuff doesn't happen where, parcel people are really throwing things around and dropping them. But the reality is, in some situations, and maybe some, lesser developed technologically supply chains, things do get handled that way. However, I would say they're the exception, not the rule. The rule, more of the rule, or the 80-20, 80%. Here's what reality looks like. This is a video, my last video here for a bit, but a video that was produced by FedEx, and it was a video that focused on inside the FedEx World Hub, which is down in Memphis, Tennessee, where all their air hub is based, and all kinds of cargo moves through this facility. And so, what does it show? It shows things moving quickly. Yeah, the video is sped up here, but the reality is this is a parcel, e-commerce / parcel type of an environment where things are moving at speed or at velocity, at high velocity. And quite frankly, the faster something moves, right, the more potential it has for hazardous types of dynamics to occur. Things moving fast, change in velocity equals acceleration. So when we talk about things like shock and impact, we talk about things in terms of G's. Well, literally, if things are moving fast and they stop, or they accelerate quickly, or other things that are moving fast bump into those items that are also moving fast down chutes and sorters, they have the potential to experience higher energy types of impact events in that certain environment. And so drop testing, I like to say drop testing really, what we use it for is determining the ability of a package to withstand the impacts that are prevalent in the distribution environment, not just those drops. Don't, open it up the scope of the kind of concept or the idea to more than just drops, right? It's really, we're using drop testers to drop package products to determine how well they'll handle various types of impacts that occur in the distribution environment or the supply chain. And why do we do that? Well, drop testers are pretty slick in some ways. Why? Because we take advantage of gravity. We take advantage of free energy, which is, acceleration due to gravity on Earth. If you drop something, we can predict, or not only predict, but control how much energy then is imparted into the item being dropped. And this is a simple formula that I'm showing on the screen that says V sub I equals the square root of 2gh. And what that really means is the impact velocity, the speed at which something hits the ground, is equal to 2 times the square root of g, which is acceleration due to gravity, which we know, it's a constant, and times drop height. So if we know how high we drop something in the real world, if you stand up and you drop something from, say, 12 inches, we know that it's going to hit the ground moving at a speed of 96, basically, let's just say 96 inches per second. Every time you drop from 12 inches, it doesn't matter. Every time it's going to hit the ground at that speed. If I drop it from 24 inches, it's going to hit the ground at 136 inches per second. And if I drop it from 36 inches, it's going to hit the ground at about 167 inches per second. Every time. It's repeatable. Why? Because we're using gravity. And so it's a simple machine. No matter who manufactures it, drop test systems are pretty simple as far as what they do. They drop items that are placed on their platens from predetermined drop heights, which allows then the user to impart controlled, energy. Quite frankly, there's another formula I'm not mentioning here, but as long as we know I think of velocity as being directly proportional to energy or kinetic energy. Kinetic energy, the simple formula is, kinetic energy equals 1/2 the mass times velocity squared. And so they are directly proportional, velocity and kinetic energy. So what we're really able to do with drop testers is control that energy that's going into a sample each and every time we drop it. This is a little calculator. We call it package dynamics calculator. That's what these 3 screen windows are at the bottom. This is a free application that we offer, Landsmont, on our website. I just put the address there. It would be the landsmont.com//support, where you can get access to this little calculator, which one of the things you can do is, might be hard to see it, but one of the tabs in this application is drop. You can calculate things like impact velocity, which is important to understand. And I'm going to come back to impact velocity and why it's relevant to this discussion towards the end of this presentation. So a little bit talking about drop testing common industry test standards. And when I mention that, excuse me, I'm mentioning that really from my perspective, or the Landsmont perspective, where we get requests for this type of equipment. Where are the references that people are asking for? ASTM 5276, excuse me, losing my voice, which is associated with a standard of how you perform drop testing and the requirements for equipment to be able to perform industry drop testing standards. I'm going to touch on that in a second, but that's very common, and it's referenced not only within ASTM, let's say D4169, but also throughout the ISTA test standards. So that's a very common reference standard for drop testing. It is, again, called upon in ASTM D4169, which really then tells you, now that you know how to do drop testing, how to actually perform it, this is the schedule of the drops that you need to perform based upon your packaged product, size, weight. It would say that you drop it 10, 11 times in these different orientations. So the schedules of how to do the drop testing is something that would be called out in ASTM D4169, very common standard around the world, as are all the ISTA standards. And so the ISTA has a number of test series that they produce and maintain. The numbers, the series number, increasing in those numbers, basically references or corresponds to an increase in the sophistication or the simulation that's part of those test procedures. But those are most common test procedures where drop testing is referenced when people are, let's say, inquiring to Landsmont. I need a drop tester that's compatible with ASTM 5276, ASTM D4169, ISTA 3A, which is a very common test procedure. And there are also company-specific standards, right? So there are a number of companies that, some are more well-known than others. Maybe might be a FedEx, might be Amazon through ISTA, but any number of companies might have their own or maintain their own drop test schedules that are, one way or the other, probably based upon industry standards, but they've modified them and controlled them themselves. They might change the number of drops or the drop heights based upon something that they know more specific about their specific supply chains or distribution channels. What are the key performance requirements, or what is the key performance requirement for a drop test system? flatness of drop. As simple as it is, it's the big issue that is important in when you're performing drop testing, when you're sourcing a drop tester. The accuracy of that flatness, the repeatability of that flatness is key. So this is a couple different ways of showing it in some drawings here, what we're talking about when we say flatness of drop. Basically what it means is when we drop a package in a flat orientation on a flat face, and that should be level with the impacting surface, when I drop it, we want it to hit in that exact same orientation, right? We don't want it to, when I drop it, it starts rotating one way or the other, from left to right or from front to back. And the reason that's important is because the severity of the acceleration upon impact that goes up, gets transmitted up through that package, changes based upon whether it's flat or not. Worst case scenario, for instance, when you drop a package in the flat orientation, is all the acceleration gets transmitted up through the package. It hits, boom, and the acceleration comes up through the package in that opposite direction. If you have any type of rotation like this, one way or the other, it can be left to right, it can be front to back, the amount of acceleration in this example that would be transmitted up through this flat surface would be less compared to this situation. And so it's important to be able to control that and to have that be repeatable in your own lab, but also across different laboratories. So if you have a company, if you're part of a company that has locations in North America, Latin America, Europe, Asia, and you all perform drop testing and you might perform it on similar types of packaging, you can actually get different test results based upon whether or not, meaning pass fail, quite frankly, or damage results, based upon whether it's dropping flat or not. And I'm aware of very specific situations where that has been the case before. And so it's called out. This flatness of drop requirement is called out as part of ASTM D5276. This is obviously too much for anybody to read, but this is where it's called out in the apparatus. Basically, the drop testing apparatus, free fall drop test equipment, says it shall permit the container to be placed on the dropping platen and experience no more than plus or minus 2 degrees upon impact, 2 degrees of rotation upon impact with the ground, or what the impacting surface is for flat drops. It allows a little bit more wiggle room within 5% for other drops such as edges and corner drops. We still, like from the Landsmont perspective, we don't. We go plus or minus 2 degrees in all those different orientations. And not only that, but every system that I'm not trying to promote necessarily as part of this webinar, our equipment, but I do want to promote the fact that every piece of, or every drop tester that we ever build gets checked out before it's ever shipped in our Monterey production facility, where we verify flatness of drop. We verify it with special equipment, photography, high-speed video, and we do it from different drop heights, front to back, side to side, and we document that. And so this is what it looks like. This is another video. I hope it shows, but you notice that the 2 different views, package falls flat, leaves flat, and it hits flat. That is what I'm trying to show there, both from the front to the back. Platen, in this case, is dropping a platform with a bag and box. Think of it like a wine bag. And you see how important it is that hit flat upon impact, so that the energy in that example all goes right through the axes that we are trying to send it through. And this is a corner drop, just to show a little bit different, but it's important, same thing, if we're going to do a corner or an edge drop, that it hits on that corner that you want it to without rotating one way or the other, so that all the mass, for instance, on a corner, the CG is right above that corner. You want it to, not only leave the platen that way, but you want it to hit the ground in that exact same orientation. So it's controlled and repeatable. So shifting gears a little bit. All right, we have drop testers. We know what's important, kind of performance for, how they operate. They need to drop flat, but how do we use them? Like how high do we drop things? What types of, do we perform corner drops, flat drops, edges? How many of them from what height? Well, we know that these things happen, right? These types of bad impacts or potentially bad impacts. I mean, no one way or the other, impacts occur in the supply chain. So we know what happens, but knowing how much is the trick. It's a simple way of saying it. And we've been saying that, or I've been saying that for probably 20 years now as part of our little marketing slogan. How do we do that? And not only just how do we, maybe as Lansmont, promote doing that, but how do people in the standards world go out and try to kind of define the unknowns that are out there in the supply chain, meaning the hazards. Yep, we use what, in our case, our savers or instruments, shock and vibration environmental recorders. That's what Lansmont manufactures. There are a number of other people, competitors or other folks that make instruments that can go out and do similar things, record shock, vibration, temperature and humidity. But an example that we're talking about here, it's really that we're trying to understand the shock or impact environment. And what savers allow you to do is measure impact acceleration events, time history events, and from that information or that data, we can characterize those events in terms of what we call equivalent free fall drops. And how you do that is there's a number of different ways. These are simple examples, but we don't just, how do you ship a saver? Well, you don't just throw it in a box. You don't just throw it in a box with some bubble wrap. You don't throw it in a box and just duct tape it to something inside that box. There's a methodology that you use for shipping these around in what would be called instrumented decoys. These are a couple examples. This is actually just happens to be a young graduate student here at Virginia Tech University who's done a lot of work and published work here recently. His name is Saewon Kim, showing some of the instrumented decoys that he put together and used for a parcel study that was performed within the last year, 18 months in South Korea. But that's what you do. You put these instruments in decoys, you ship them around in the supply chain, and you get data from those impact events, and you use or you look at that data and you characterize it in a specific way to say, oh, that was a big impact that occurred Tuesday at 2 o'clock in the afternoon, and it's the amount of energy that occurred in that impact was equivalent to what I would generate if I dropped that package from 16 inches or half a meter. That's how we characterize those types of events. How do you really do that? Defining those unknowns. It sounds, maybe I'm way oversimplifying it when I say that. There is a lot of work that goes into those types of projects where you characterize the environment, as far as how you use the instruments, how you set them up, and how you collect data. So what I'm just sharing here real quick is ISTA recognized that once upon a time that there was an opportunity for them to create something called data collection standards that basically said, hey, people, we value this type of information wherever it comes from, whosever instrumentation it might come from. We value it because it drives our testing standards, the development and maintenance of our test standards. However, we think there's a right way, right way to collect that data and incorrect way of collecting that data. So they set in motion through the organization to create what are called data collection standards. And so this is just some screen captures to show what they've done is they've collected standards that say if you're going to collect shock and impact data and drop equivalent free fall drop height data, or even vibration data, here's how you set that instrument up. Again, too much to read. I realize even some of the quality of these images is not that great. But what these documents do is they tell you how to set up your data recorder. And again, these are manufacturer agnostic standards. So they work not only with, say, a Landsmont data recorder. You could use these no matter whose instrumentation that or data recorders that you would have to go out and collect information of quality, that could be used or actionable moving forward. So these are really a nice effort that says, if you're going to collect it, here's how you do it. Very helpful. And then along those same lines, once you've collected it, that data, data is just data, right? It's might be tough. It is tough. It can be challenging for how to interpret that data, make sense of that data. Well, ISTA also has what they call data analysis guidelines. And so I'm just sharing, a couple pages to what that looks like, but data analysis guidelines for shock, impact, and drop data. How you collect it, or not how you collect it, but how you view it, how you summarize it, how you perform statistical analysis of that data, which is another powerful tool for anybody that wants to go out and do these types of studies. If you want to do it, these are great reference documents that you have access to if you're ISTA members, and you even have access to them if you're not an ISTA member. You can purchase them, but they're free if you are members through their technical library. So, quick video again of dropping a box, right? So here's, dropping a box on its corner. And what I'm going to show is kind of an example of what data looks like when you measure that. So this is obviously something that was dropped in a laboratory on a drop tester. But when we drop something on its corner, for instance, in this example, what we really get from the data recorder is data that's coming back from a triaxial accelerometer. That's normal for what you might use even for laboratory data collection that you could do during your drop testing, or through instrumented drop testing out in the field. And you get different channels, right? You're able to record in different directions, X, Y, and Z with it. For instance, with a triaxial accelerometer, which means, X, Y, and Z means up and down, side to side, and front to back in those directions. And so when we drop something, for instance, on its corner like this, in this example, and I have an instrument inside that package, I'm going to record acceleration time history waveforms in those three different directions, up and down, side to side, and front to back. And that's what you're seeing there with the three traces that are the three different directions overlaid on top of each other, right, in the same time window. And what we get from acceleration is a vector. From a physics perspective, it's a vector, which means it has direction, right? So acceleration has direction. So that's powerful. So when we look at these triaxial triaxial waveforms, we can calculate what's called the triaxial resultant, which you can probably see here is a white trace, which is a vector sum. It's a summation of the three channels, which gives us the overall magnitude of that event, but it also gives us direction. So one of the other windows that calculations that we can look at here with our instrumentation from the field, data recorders, the savers, is called the vector visualizer. So what you see in this example is this white trace, right? This white trace, if I translate that over here, you see a white trace here, you see a white trace here, and you see a white trace here. That white trace is basically giving you the direction of how that energy, the impact energy, entered into the instrument. So, in this view, this is a top-down view. You can say, well, it's coming from that. It looks like it's came into the front right corner, and this basically says the same thing from the front right corner, but this one says it's the front bottom right-hand corner, right? And that's exactly what you see is called out from the, basically the automated, analysis of that vector visualizer. It says, yeah, that was a impact on the corner, the right front bottom corner. And that all comes from analysis of those triaxial acceleration waveforms that you get when you record impacts with these types of devices. And not only that, but you get key information associated with the magnitude, let's say, or the intensity of that event. So when here's that same waveform, but if I focus the information down at the bottom, what that is telling me for that vector sum, the white trace, it says, well, adding all those up together, that says the package saw 20, let's just say just over 24 Gs on that bottom right hand corner, lasted over 38 milliseconds, almost 40 milliseconds, and it had a velocity change, which is back to, remember, where I shared earlier. That's a number that we can kind of associate with what was the intensity or the severity of this measured event that we measured during our drop testing or maybe out in the field. And we can say, oh, wait a minute, you say that impact right there has an overall velocity change of nearly 170 inches per second. Well, if I back calculate, this is an oversimplification, but this is really kind of how we do these types of field studies. If I back calculate, I can say, well, based upon what I'm seeing in this field data, it looks like that impact had the equivalent energy, this comparison to this comparison, of about a 36-inch drop. So that would say, if I wanted to simulate that, let's say this was captured somewhere out in the field, if this was captured out in the field, the way I would want to replicate that or simulate that would be to drop it from the drop tester on its front right-hand bottom corner from 36 inches. So there is kind of a method to that madness. And that's really what's spelled out even in the ISTA documents, ISTA data collection guidelines and the ISTA data analysis standards. And just to show you some examples, so just so happens, again, this is a study that was done recently and published recently by Se-Wan Kim here, the graduate student, and the folks here, a group of folks at Virginia Tech University. But it's a real example of somebody that has gone out and done these kind of field measurement studies. So this in case says measurement and analysis of the shock and drop levels experienced by small and medium packages in the Korean parcel delivery system. You see again instruments using the instrumentation, but also these instrumented decoys that talks about how they went about it, how the decoys were set up, and the distribution routes. So in this case, it's hard, a lot of detail here, small, but in this case, 60 different instrumented decoy shipments, which is, might not sound like a big number, but that actually is a pretty significant overall study in the amount of data that it generates and statistically valid. This gives you an idea of somebody that would go out and do this with different decoys and different replicate routes and then publish this information. So people, example of somebody doing the study of supply chain parcel shipping in Korea. And another big one that I would just mention is this ISTA Advocate Single Parcel Project that has been in process for a number of years. Actually, it's done. The the actual instrumented shipment is done. We're within ISTA in the final stages of summarizing all the data that was generated from this study. But this was a big study that project background and objective, wanting to know if drop heights and the number of drops, the frequency of drops were affected by package weight, package size, the carriers, the distances and destinations, and then eventually, look at how all that data would compare to the current existing ISTA 3A drop testing schedules. And so the same thing, a number of different instrumented decoys, different sizes that were used to ship out. And the size and scope is one of the things that I really am impressed by. So this was something that was eventually ISTA contracted with both RIT and Michigan State to do this research, but they did a total of over 1,000 different instrumented shipments over about a 2-year period, with a number of different size decoys, what we would call standard, kind of cube size decoys, rectangular size, flat shapes, elongated shapes, and different weights within each of those categories. And then not only that, but then shipping through 3 different distribution systems: UPS system, FedEx system, and the U.S. Parcel Service, U.S. Postal Service, excuse me. So this is a large scale project, generating really meaningful statistical valid data that's going to be at some point here become more, in the one way or the other, have an impact, no pun intended, with ISTA's industry standards. It's going to be referenced, and looked at as far as what, if anything, needs to change based upon the results we saw from the measured data. So it's just another example of a large-scale study that people go and kind of set the methodology for how you do drop testing. And it's not only that we understand, let's say, what the drop heights are, right? So drop height is, or the equivalent drop heights, meaning the intensity of them, is important. But what you also get from doing these studies is how many of those drops, kind of percentage-wise, what's the allocation of those impact events, drops, equivalent drops? How many of those were from the flat orientations that came in through the flat faces of a package? How many came through, percentage-wise, through the edges? How many of them were corner? And, not only just like flat, which flat faces? Was it from the left side, the right side, the bottom, the front, the back? So we can really get into, good resolution on understanding how, these drops or these events were experienced. And it's not, absolute as far as when we say a corner drop. Does that mean literally on the corner? There's really no great way to define that when you send out, some of these instrumented packages out into the real world. So when we say corner or edge or flat drops, the way I like to describe it was like a flat-like drop, or a edge-like event, or a corner-like event. It's not absolute, but it means most of the energy came through the corner as compared to coming through an edge or through a flat surface. So we are able to really start to characterize, again, what the equivalent drop heights are like in an environment, the drop orientations, how those events are experienced in supply chain, and the numbers of those events that occur, so that we can use that to set our drop schedules. And we can use that information to compare, right? So that's what is a very common thing that I get involved in with companies, is they say, listen, I'm using some existing standard. In this case, I'm just referencing just the general drop schedules for ISTA 3A and for 4169 distribution cycle 13. In ISTA 3A, there's 17 drops required total. If you went through the full ISTA 3A procedure, 15 of them from 18 inches, 2 of them from 36 inches. So how does my, if I go out and do one of these studies from my supply chain, how does my data from my supply chain compare to this data? Do I want to change because of that? Or do I want to change and create my own customized test procedure for my company? Or might I advocate through ISTA or ASTM to change their test procedure based upon this data? But one way or the other, that's what a lot of people do, is they compare, they're comparing, going out and saying, here's, my standard testing approach is this, ISTA 3A. I want to see if that is still valid, one way or the other. Is it still valid and representative, or do I need to consider changing it in one direction or the other? And then the other thing I would say is not even collecting literal impact data, equivalent free fall drop data from the real world is important, but just as important is observation, right? Meaning visual observation, or that you can document with your eyes, document maybe with camera, document with video. So for instance, if I'm going to go out and do a bunch of measurement, shipping decoys around packages, and I get all these, take pictures of how they were shipped and how they were received, and I kind of think of that as how it performed in the real world. Well, how does that compare to when I do laboratory testing on that same package? When I do laboratory testing, does it correlate? Is the damage that I see in the field or lack thereof similar to the damage I experience or lack thereof in the lab? Is it correlate, or does it not correlate? Quite frankly, that is important to understand. So not just going out and doing all these measurement studies where you're getting all this data from data recorders, but what does it look? What does the package look like? What does the transport package look like? What does the internal packaging look like? Obviously, what does the product look like? But this is important, in my opinion, for closing the loop to say, is my drop testing approach representative? It's not just the ability to do these kind of more comprehensive and challenging field studies with data recorders, but just how about the observations? Do you ever see this type of damage, which was generated from testing in the lab? Do you ever see that in the real world? I have examples of people that I'm working with where they've looked at that. In looking at over a number of shipments that would total, international shipments that total over 1 million shipments, the documented damage through a pretty well maintained documentation program said there was about 38 damage cases that were filed out of about 1.5 million shipments. Out of that 38, half a dozen of those could be really looked at and called likely impact related damage, as compared to other things that might be like tearing or abrasion related damage. So that type of information is critical, when you might say, maybe we should change our schedule. Maybe we should lower the drop heights. Maybe we should reduce the total number of drops that we're performing. It's not just based on the waveforms that we're getting from the field that look comparably lower, but it's also from observational data, right? If you basically get 38 out of million or 1.5 million, that says maybe there's an opportunity to have some confidence in changing your test procedures. So this is just more videos showing, lucky enough to have equipment at Amazon, and you can look at equipment at Amazon, drop test equipment at UPS. You can see the amount of testing that takes place at these facilities. These are in cases people that are retailers or people that are involved as carriers in the supply chain that deals with parcel and maybe e-commerce situations, and they use awareness of their own systems to drive the type of testing they perform, or have their customers that ship through their supply chain perform. It's based upon the knowns within their systems, and it drives their company, either their company test standards or industry standards that are referred to that address their supply chains. And one of the other things I wanted to mention, unfortunately, unfortunately, concurrent to my webinar, come to find out there was a ISTA digital webinar that was taking place today that is highlighting this new program or new platform that ISTA is rolling out, in the process of rolling out, called ISTA Digital, which really basically, you know, what's relevant to this conversation means is they're developing an application that will allow data to be input into their system. Again, agnostic to any manufacturer's data recorders. It's not about data recorders. It's about the data that is generated from those, the summaries from those. But the ability to take, you know, mass quantities of data from different companies that might do these studies and summarize that on a much larger scale, and then use that data to help drive development of not only test standards, but even to have influence on package design moving forward. So I wanted to mention that because I think it's a new, you know, nice, powerful tool that also is going to be rolling out here very shortly, that can be fed with data from any number of sources, but then be able to output actionable test schedules and test plans based upon all that data. So I'm just about done. I just wanted to mention, you know, this is the first of 2 webinars that I'm going to be delivering. This was really to talk about the application of drop testing. And the next webinar I'm going to be talking about is really our products that we offer to perform drop testing, specifically, you know, free fall drop testers, one way or the other, that cross different performance and different range of capabilities. And I'm going to be delivering that live product update on 2 weeks from now, Wednesday, August 7th. And that will be done from a laboratory at Michigan State University. So I'll go back to Michigan and do this from Michigan State University, where they have one of our PDT 300s and PDT 80, which are the 2 drop testers you see on the left. So I'll be able to demonstrate those, the key kind of components and features associated with that type of equipment, how they operate, and even show some things like associated with instrumented drop testing. So not just dropping a package, but how you can instrument what's inside the package. So you can take testing from like a pass-fail qualitative assessment to a measurable quantitative performance. You know, you can actually do quantify the performance of your packaging to say, is it better or worse than this, you know, this iteration number 2, iteration number 3 with a different design? Am I getting better or am I getting worse, and can I quantify that? So I'll be touching on all that Wednesday, August 7th. And then last thing I wanted to mention is one of our PPT partner companies, McMesson, who provides kind of benchtop equipment, universal test systems you can think of for performing things like edge crush, carton crush, tensile, more of the materials testing side of things. They tomorrow have a webinar focused on edge crush and carton crush testing. And so I wanted to mention that because it's relevant to what we do at Lansmont. Yeah, we are more of the performance testing of the transport package, the fully constructed package, sometimes the packaged product. But you know, our partner PPT companies also get involved in the material side of it, or you know, some of the components associated with the transport packaging. So they're hosting a edge crush and carton crush testing webinar tomorrow. So feel free to join if you would like. I think Sharon will know here in a second. I see the chat being highlighted. There might be a link to the registration for that webinar in the chat. And with that, I'm going to stop talking and open it up for questions. Apologize if I ran a little bit long, but I guess I'm not too upset with my timing. So I'm happy to entertain some questions at this point. And Sharon, I take it you can join back in.
Thanks so much, Eric. Yes, I have dropped the next drop testing webinar, the details for that in the chat box. If anybody wants to join, and like Eric said, now would be the time to submit your questions, and we'll just give it a few minutes to see, you know, has anybody got any questions that they'd like to raise or discuss. And then in the meantime, what I'll also do is find the actual link to the edge crush and carton
Oh,
crush test webinar, and I will
okay.
also put that in the
Yeah, sorry to put you on
chat
the spot
box
with
for you.
that,
No,
but
no, I mean, it's much better, much easier if I do it that way.
yeah, okay.
Okay, I can see a question. Let me just take a look. I just want to highlight that. Okay, Eric, this is you. What are the key factors to consider when selecting a drop tester for a specific product or industry?
Well, the size, the footprint, so the physical dimensions of what you're planning to drop, which doesn't necessarily just have to be a package. Drop testers, PDT for us means precision drop tester. We also, some people refer to them as package drop testers, but you can drop other things. You can drop bottles from there. You can drop bags from those. You think of, like I showed a picture of a bag in a box, but you can drop bags of like pet food. I've got videos that I can share that show those type of applications. So really the footprint matters, right? For how big of a platen, meaning how big of a platen that would hold your product before you drop it. And then the other key criteria is the weight. So that we are drop testers. So again, getting ahead of the next one I'll doing, but our drop testers PDT 80, PDT 300, PDT 700. The number there is associated with the maximum payload in kilograms. So PDT 80 can drop upwards of 80 kilogram samples, 300 kilogram samples, 700 kilogram samples. So those are the kind of key criteria. And you can within some range, you can even change the drop heights, but it's the drop heights are more based upon what, how high you really feel like you need to go. But what drives the strength and bulkiness of a drop tester is how big is your item that you're going to end up testing, the maximum that you're going to want to test, the footprint size and the weight. And we can do different things to account for ranges there. We make different size platens for all of our drop testers. They can be extended widthwise, they can be extended lengthwise to allow for different configurations within range or within limits. And obviously so those you can go bigger with platens in the same product category, like a PDT 80. But if you the weights, if you change the weight up anything greater than 80 kilograms, so you got a 150 kilogram item, you're going to need to step up to the 300 if you want to be able to drop that. And then you still have different platen size options in that specific model. And then the same for the 700, which is the big heavyweight one, the really big heavyweight one. Different platen size options for that, depending on how big you're going to drop. Hopefully, I'm starting to repeat myself, but don't know if that answered the question or not.
I've got a follow-up question from the same person, actually. How do you ensure the accuracy and repeatability of drop test results?
Well, we use camera equipment when we check everything out in our shop, and we can do that in the field for people. If you really think about it, it's not just Landsmont. So the ASTM 5276 specifies the flatness of drop. And we validate it, verify it, document it on everything that we build. But can it change over time? Can it change when it's installed? Can something be out of whack? Yes, it can change, and there are ways for us to do that same verification in the field. And individuals could do it as well with high-speed video. Doesn't need to be crazy high-speed video, but basically dropping and measuring to a reference, let's say level. So you're measuring as it drops and taking basically having enough frames to see the drop level, and then enough frames to see when it hits. Is it dropping level, or is it did it drop flat and now it's rotated when it hit the ground? And so plus or minus 1 degree of accuracy is, or 2 degrees of accuracy is pretty tight, pretty difficult to do. Plus or minus 5 degrees is a little bit easier, but you can do it with these days high-speed video, and even, I don't know, 500 frames per second, you could do something like that on your own. But we do offer it. Our service group can do it. We have the ability to go around with equipment on our end to document those things.
Thanks, Eric. I think that is everything for now. Just a reminder that we will share the recorded video with you, which obviously showcases all the slides and everything that Eric shared today, and the videos, like he said, he overlays again. So they should be good quality. And if you feel you have further questions that you'd like to discuss with him, you can see that his email address is on the screen at the moment, eric.jonassen@pptgroup.com. The last thing I would say is we hope to see you again at our next webinar. So yeah, thanks, Eric. We hope to see you again at our next webinar, and that's happening on August 7th, and that will be the conclusion of this series, as Eric mentioned. That's the live demo of the drop testers.
Yeah, and that will be from a laboratory, and we'll have cameras, more than one camera, and we've tried this before. We've had success and limited success, but it's going to work perfectly fine where we'll have multiple cameras involved next time. So not only can you see a drop tester and from afar, but I'll be able to tour around these systems and talk about key components and basically how they work. And there are differences between the two, the lighter weight ones and the heavier weight ones. So we'll get into more detail about the specific machines during that event, and leave more time for questions about the specific machines and types of machines at that point. So thank you. Thanks for your help as well, Sharon, today.
Pleasure. Thank you very much, everybody. We're going to end the webinar now, and we hope to see you again. Thank you. Bye.
Thank you.